Hello, in this video we are working through example 3 in section 8.4. Specifically, we're on day 2 of 8.4, so we're talking about absolute convergence. In example 3, this says to show that the series the sum from n equals 1 to infinity of negative 1 to the n plus 1 over the square root of n is conditionally convergent. So remember, from the notes just above this example, that in order to show something is conditionally convergent, so to show conditional convergence, we need to show two things. So first, we need to show that the series does not absolutely converge. So in other words, that means that our series of absolute values, so the sum of the absolute value of n, diverges. We must show that. And second, we need to show that the original series does converge. Now, the original series is alternating, which means that we are going to have to apply the alternating series test in order to show that it does converge. Now, either one of these things that we need to show can come first. The order really doesn't matter. You can show that the series of absolute values diverges, and then the original series the original alternating series converges, or vice versa. Like I already said, the order doesn't matter. But I personally like to look at the series of absolute values first, and the reason for this will become a little bit more apparent later on in the lecture, but mostly it comes from the fact that if you don't know whether the series converges conditionally or converges absolutely, so in other words, imagine if this problem said show that this, or determine whether this series conditionally converges or absolutely converges. You don't really know which option it is. In that case, then it's a lot easier to start with this option. Okay, so that is where I am going to start here in this problem. So for one, we're going to look at our series of absolute values. So we're going to look at the sum from n equals 1 to infinity of the absolute value of negative 1 to the n plus 1 over the square root of n. And just like in the previous example, the denominator is always positive. Square root always gives you a positive value. The numerator is going to be either negative 1 or positive 1, depending on what our power is here. So when we take the absolute value of that, it's just going to give us a 1. So we end up with the sum from n equals 1 to infinity of 1 over the square root of n, and we can write that as the sum from n equals 1 to infinity over of 1 over n to the 1/2. Again, this is a p-series. P is equal to 1/2 here. P-series converge depending on whether the p-value is greater than or less than 1. In this case, p is strictly less than 1, so that means that it does diverge. So this in combination, the series of absolute values diverges. So this means that the original series, the sum from n equals 1 to infinity of negative 1 to the n plus 1 over the square root of n, does not converge absolutely. And that is one of the things that we need to show in order to show conditional convergence. The second thing is we now need to look at the original series, apply the alternating series test, and show that it does converge. So for 2, we will apply the alternating series test. For the alternating series test, we need to look at the magnitude of the terms. So in other words, we're going to take an, which is the entire thing, negative 1 to the n plus 1 over the square root of n. If we just drop off that alternating piece, then we pick up the magnitude of the terms, and this is what we look at for the alternating series test. So bn is 1 over the square root of n. Remember, with the alternating series test, we need, again, two things. So first, we need the limit as n goes to infinity of bn to be 0. So we need our terms to be going to 0. And second, we need our terms to be decreasing. bn plus 1 should be less than or equal to bn. So then we will look at both of those things here. So let's notice we're going to look at the limit as n goes to infinity of 1 over the square root of n. Well, the numerator is constant, the denominator is getting larger and larger, so very clearly that, and very simply, that just goes to 0. No more work is needed there because it is easy enough to simply state that that is going to 0. So that's one thing to check off. The other thing is that we need to show that our terms are decreasing. Best way to do this is to look at the function with the same values and show that this function is decreasing. With calculus, we can take a derivative, show that it's negative, and we get that it's decreasing then. So this means that f prime of x, let me write it this way. We can rewrite our function as, x to the negative 1/2. So this will mean then that f prime of x is a negative 1/2 x to the negative 3/2, or we could write that as negative 1 over 2 x to the 3/2. In this case, since we are talking about f of x coming from this 1 over the square root of n is always positive, so we could think of x as being bigger than or equal to 1. This means that x to the 3/2 will always be bigger than or equal to 1, which means that 1 over 2 x to the 3/2 always bigger than or equal to 1/2 if you really wanted to say that, but it's definitely going to be positive, which means that f prime of x, which is a negative of all of that, 1 over 2 x to the 3/2, that's definitely going to be negative, which means that the function is decreasing. But since we got this function from what our terms looked like, it means that our terms are decreasing as well. And that's the same thing as saying that bn plus 1 is less than or equal to bn, and this is true for all n greater than or equal to 1. Okay, so that is the second piece that we need for the alternating series test. As long as we have that the limit of our terms is 0 and that our terms are decreasing, then by the alternating series test, the series converges. Now that's just normal, plain old convergence. There's no conditional or absolute descriptors there on the convergence. Alternating series test just proves regular convergence. But this result, in combination with the fact that this series does not converge absolutely, that is the definition of conditional convergence. So we can make our final conclusion. Therefore, the sum from n equals 1 to infinity of negative 1 to the n plus 1 over the square root of n converges conditionally because it converges but does not converge absolutely. But does not converge absolutely. And there we are done for example 3.